Hello students, today we will discuss about relation. Okay, so before I define what is relation, at first we have to know what is Cartesian product. Okay, let U be an universal set, okay, and A be two non-empty subsets. Okay, then we define and denote Cartesian product of A and B is A cross B. We denote it as A cross B and defined by A comma B such that A belongs to A and B belongs to B. Okay, let me clear this definition properly. See, if A is 0, 2, 3, 4 and B is A, B, C, D, then the Cartesian product of A and B is the set of all ordered pairs. Okay, where the first component, this is called first component of the ordered pair, this is called ordered pair, and this is called second component of the ordered pair. So here A cross B, so at first in the place of first component we have to put A's element, okay, and in the second component we have to put B's element. So at first if we put in first component 0, then the possible ordered pairs are 0 comma A, okay, 0 comma B, 0 comma C and 0 comma D. Fine. Now if we put the element 2 in the place of first component, then the possible ordered pairs are 2 comma A, 2 comma B, 2 comma C, 2 comma D. Okay, and continuing in this process we have the full list of elements, and these are the elements are end with 4 comma A, 4 comma B, 4 comma C and 4 comma D. Okay, so this is our Cartesian product of two subsets. Now if we have 3 or 4 or n many subsets, then we can define also the Cartesian products of n many subsets. Okay, let a1 a2 dot 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 an be n finite subsets of U, then Cartesian product of a1 cross a2 cross dot 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 cross an is defined by a1 a2 dot 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 an. Okay, this is called n tuples. This is called also this is called two tuples, but we call this ordered pair, and this is called n tuples, such that a1 belongs to a. Okay, a2 a1 a2 belongs to sorry this is wrong. A2 belongs to a2 and an belongs to an. Okay, so this is all about our Cartesian product, and now we can define our relation. What is our definition of relation? Okay, now we are able to define what is relation. Okay, relation. Let S and T be two non-empty sets. Okay, a relation, or we call a binary relation, a binary relation rho. Okay, this is called rho between S and T is a subset of S and S cross T. Okay, so what is relation rho, rather binary relation rho? Rho is a binary relation between S and T, is a nothing but a subset of S cross T. Okay, see, let me clear the definition by some examples. Okay, example 1. Okay, let S be the set of all students. Okay, and T be the set of all teachers of our college. Okay, let rho be a relation between S and T defined by specifying that S, small s in capital set S is related to a teacher T in T if S happens to be a student of T. Okay, see, I have to say some words. See, since rho is a subset of S cross T, then rho is of the form, okay, where S belongs to S and T belongs to T. Fine. So we call the ordered pair S comma T as S is related to T. S is related to T by the relation rho. Okay, say if S belongs to capital S and small t belongs to capital T, then S comma T is an ordered pair of S cross T, Cartesian product of S cross T, and we call the ordered pair S comma T as S is related to T by the relation rho. Okay, this relation rho is usually a mathematical relation, okay, in our mathematics, but in the example 1 I will explain the relation by social relation. Okay, let's see. If S happens to be a student of T, then here the relation is the student teacher relation. Okay, so it may be that a particular student say S1 in S is a student of teachers T1 and T2, but not T3. See, we are considering that a particular student S1 in S, set of students in S, is student of teachers T1 and T2, but not T3. That means S1 is a student of T1 and T2, okay, but he or she is not student of T3. Then see here, rho is the relation student teacher relation. Okay, if S1 is a student of T1, then S comma T1, this ordered pair, belongs to rho. Rho is a subset of S cross T. But if S1 is not student of a teacher, say T3, yeah, T3, then S1 is not related by the student teacher relation with T3, and hence S1 comma T3 does not belong to our row. Okay, see, then S1 and T1 and S1 comma T2, these are only the ordered pairs, okay, belongs to row. Okay, but S1 comma T3 does not belongs to row because S1 is not a student of T3. Okay, so we have to clear our concepts that if S is student of T, then S comma T is one of the elements of row. Row is a subset. Okay, and if S is not student of T, then S comma T, the ordered pair, does not belong to our row. Okay, remind it, row is a nothing but a subset of S cross T. Here S is the set of students and T is the set of teachers. Okay, and we call row as a student teacher relation. Fine. Okay, I hope you can understand. Okay, so here I am considering the example 2. Okay, see, if S is equal to the set containing 2, 3, 4, 5 and T is a set containing 11, 12, 13, 14. Okay, and row be a relation between S and T. Okay, defined by an element S in capital S is related to an element T in capital T if S is divisor of small t. Okay, see, so our S is this and T is this, and row B a relation between S and T defined by an element S in S is related to an element T in T if S is divisor of T. Okay, so let me do this. See, at first I am considering the Cartesian product of S and T. Okay, okay, here S is 2, 3, 4, 5 and T is 11, 12, 13 and 14. Okay, at first we are considering the Cartesian product of S and T. Okay, let me write all of the elements of the Cartesian product. Okay, so in the place of first component I am writing the element 2, and the possible ordered pair, so the possible ordered pairs having 2 as a first component are 2, 11, 2, 12, 2, 13 and 2, 14. Okay, now the ordered pairs having 3 as a first component as 3, 11, 3, 12, 3, 13, 3, 14. Okay, now 4, 11, 4, 12, 4, 13, 4, 14. Okay, and at last 5, 11, 5, 12, 5, 13 and 5, 14. Okay, so this is my complete list of elements of Cartesian product S and T. Now rho is a relation, okay, where S and T are related by if capital is small s is an element, if small s is an element here, if small s in S is an element is related to an element T, small t in capital T, if S is divisor of T, that means now we are considering our rho. Here rho is subset of S cross T. Okay, and in rho those elements are there which are related by division relation. Okay, see, at first I am looking at 2, 11, the ordered pair. See, here 2 is not a divisor of 11, so this ordered pair does not belong to rho. Now 2, 12, here 2 is divisor of 12, so 2, 12 is in rho. Okay, now 2, 13 is not divisor of 2 is not divisor of 13, so 2, 13 does not belong to rho. Okay, see, 2, 14. Okay, here 2 is divisor of 14, so 2, 14 belongs to rho. Okay, now if we continuing the argument, this argument, then we have the list of rho 3, 12 and 4, 12. Okay, so in these all elements we have only 4 ordered pairs in which first component is related to second component by our division relation. Okay, I hope you understood the relation. Okay, the concept of relation. Now we are defining domain of row. Okay, domain of a relation row. So we denote domain of a relation row by D of row and defined by A such that A belongs to capital A and A comma B belongs to row. The domain of the relation row is nothing but the collection of first components of the ordered pairs which are belonging into the row. Okay, and the image of a relation row by Im of row, and this is equal to B such that B belongs to the capital B and A comma B belongs to row. That means Im of row or image of row is the collection of all second components of the ordered pairs which are belonging into the relation row. Okay, now we are defining the inverse relation. Okay, inverse relation. Let row be a relation between two sets A and B. Okay, the inverse relation of row is denoted by row inverse and defined by row inverse is equal to B comma A such that A comma B belongs to row. So row inverse is nothing but the collection of those elements, okay, whose flipped version is in the row. Okay, just you have to flip the elements of row, and then you get a new ordered pair, new collection of ordered pairs, and that collection of ordered pairs is called row inverse. Now more results of relation. Let rho and sigma be two relations between the sets A and B. Then clearly rho and sigma are the subsets of A cross B. Okay, and since rho and sigma are the subsets of A cross B, so rho union sigma and rho intersection sigma are union and intersection, okay, respectively. Okay, see, I have given the definition of a relation rho between A and B, where A and B are distinct. Okay, I didn't say that that A and B are distinct, but without loss of any generality, we may assume that A and B are distinct. But sometimes we can take A and B equal, okay, and in that case our definition will be same. Okay, let S be a non-empty set. Okay, non-empty set. A binary relation rho on S is a subset of the Cartesian product S cross S. Okay, that means that is, if A comma B belongs to rho where A and B belongs to S, then A is related to B, or we can write A rho B. Okay, A rho B. Okay, now I am going to discuss the most important part of relation. Okay, that is equivalence relation. Equivalence relation. Let S be a non-empty set. Okay, non-empty set, and rho be a binary relation. On S. the relation row is said to be reflexive if a comma a, the typical ordered pair a comma a, belongs to row for all a in S. That is, a row a holds for all a in S. Okay, see, this is a very important line. That is, the relation row is said to be reflexive if a comma a, the ordered pair, belongs to row for all a in S. That is, a row a holds for all a in S. That means if S has 3 elements, okay, so and let me assume row be in relation on S, okay, that means row is a subset of S cross S, okay, then row is then if 1 comma 1 2 comma 2 and the element 3 comma 3 all are belong to row, then row is reflexive, okay, then row is reflexive, okay. If one of the elements does not belong to row, then we cannot say row is reflexive. Okay, this is 1, this is 2. The relation row is said to be symmetric if for any two elements A, B in S, okay, if A comma B belongs to row implies B comma A belongs to row, okay, that means if A comma B belongs to row implies B comma A belongs to row, then row is symmetric. See, let me take an example. I am taking the similar set S, okay, and row in relation on S. Then if 1 comma 2 belongs to row implies 2 comma row belongs to row, then row is symmetric, okay. See, you have to observe properly that here if row has to be symmetric, then then this condition this condition need not to be hold for all elements of S. Okay, if a comma belongs to row and if we find b comma a belongs to row, then row is symmetric. But if we find a comma b belongs to row but there is no b comma a in row, then we cannot say that row is symmetric. Okay, now I am writing here three. This is 3. The relation row is called transitive if for any 3 elements A, B, C in S. A, B, C in S. If A comma B belongs to row, B comma C belongs to row, implies E comma C belongs to row. Okay, that means if we see that A, B, C belongs to S and A comma B and B comma C belongs to row, and we find the element A comma C is also belong to row, then we can say row is transitive. But if A comma B belongs to row, B comma C belongs to row, but A comma C does not belongs to row, A comma C does not belong to row, then we cannot say the relation is transitive. Okay, and the last line of our definition, if row is a relation on S which is reflexive, symmetric and transitive, then row is called equivalence relation. Okay, just you have to remember these things, that if row is a relation on S, which is reflexive, symmetric and transitive, then row is called equivalence relation. See, now I am doing a problem on equivalence relation. Okay, a relation row is defined on the set Z. Z is set of all integers. Okay, by A row B holds if A minus B is divisible by 5. Okay, A row B holds if A minus B is divisible 5 for A comma B belongs to Z. Prove that row is equivalence relation on Z. That means we have to prove that row is reflexive, symmetric and transitive. Okay, number 1, let A belongs to Z. See, when we are showing row is reflexive, then we have to show that for each A belongs to Z, the ordered pair A comma A is also belongs to the relation row. Okay, see, now A minus A is divisible by 5. Why? Because A minus A is 0 and 0 is divisible by every real number. Okay, so A minus A is divisible by 5 and our relation is if A minus B is divisible by 5, then A row B holds. So A minus A is divisible by 5, then by the given relation A row A holds. So A row A holds for all A belongs to Z, because whatever A is, if we take A minus A, then A minus A is 0 and 0 is divisible by 5. So A row A holds for all A belongs to Z, and this implies that row is reflexive. Okay, now we have to check that row is symmetric. Let A comma B belongs to Z. Okay, and A row B hold. See, just recall the definition of symmetricity. In the definition, A and B are from the Z, are from the S set S, and we have to assume that A row B hold. Then if we show that B row A holds, then we can say row is symmetry. Okay, see, A row B hold, A row B holds means A minus B is divisible by 5. See, if 5 divide any number, okay, sorry, if 5 divide a number, whatever it is, positive or negative, if 5 divides A, then 5 divides minus A also. Okay, so by this argument we can tell that B minus A is also divisible by 5, and hence we can tell that we can say that B rho A holds and rho is symmetric. Okay. Number 3. Now we have to check rho is transitive. Let A, B, C belongs to Z, and here we have to assume that A rho B and B rho C hold. Okay, so we have to now show that A rho C hold. Now A rho B and B rho C hold means A minus B is divisible by 5 and B minus C is divisible by 5. Okay, now we have to show that A minus C is divisible by 5. Okay, so these two lines imply that A minus B plus B minus C is equal to A minus C, and if if 5 divides X and Y, then 5 divides also X plus Y. Okay, these are very elementary things. So by this argument we can say that A minus C is divisible by 5, and hence A rho C holds. So rho is transitive. Okay, and from 1 to 3 we can say that rho is equivalence relation on Z. Okay, so if you are given that a relation rho is equivalence or not, you have to prove that, then you have to approach the problem like this. Okay, problem 2 is a relation rho is defined on Z, that means our suitable integers, by A rho B holds if AB greater than 0 for A comma B belongs to Z. Okay, then show that Rho is not equivalence. Okay, see, we have to show that rho is not equivalence. So if we show that rho is not reflexive or not symmetric or not transitive, then we are done. Okay, so we have to check that one of the three relations is not holding. And we have to check that one of the three relations does not hold. Okay, see, let, so we have to first check that A is reflexive or not. Okay, let A belongs to Z, then A dot A greater than 0 if A not equal to 0. That means if A is 0, then 0 into 0 is equal to 0. But to show rho is reflexive, we have to show rho is reflexive, this relation must be hold. That means to see rho is reflexive, we have to show that A dot A greater than 0 for all A belongs to Z. But here, if A is 0, then this relation is not true. So if A equal to 0, then equal to 0, hence A rho A does not hold for all A in Z. Okay, so rho is not reflexive. Okay, see, we don't have to check all the relations, all the three relations, because at the first stage our checking rho is not reflexive, so hence rho is not equivalence. Okay, I am giving you homework that check rho is symmetric and transitive. Okay, so this is all about relation. Okay, so in the next class we will discuss about mapping. Okay, so I am stopping my class here.